So I will talk about some of the experiences regarding Fugaku. Now that's a year into operations, what are the lessons learned? And of course, I really can't go into the details. As Tomita-san explained, there's a whole symposium is dedicated to that. So you will hear lots of excellent, fantastic research results, both from applications as well as from computer science research. But I'll highlight a few, but then really spend the remaining half of my talk regarding observations towards the future as we progress our computing for both non-quantum and quantum future. So before I proceed, I'd like to say a few words about the passings of our beloved colleagues in HPC. One person is Professor Hiroshi Nakashima at Kyoto University. Unfortunately, he was in a bad traffic accident, and unfortunately, he didn't survive. He was our colleague for a long time, not just me, but Sato-san, Ishikawa-san, etc., with whom we really did research to create foundations of some of the infrastructures we have, including Fugaku. So he was still in his prime, and it's really unfortunate he's passed away. Also, Professor Puchong Dayapas, who's also our dear friend for a long time. He was a big partner in our ambitions to expand our partnership to Asia, ASEAN countries. And just as Thailand was getting its first supercomputer with a very credible international presence that he had worked on for the past 20 years with and had a little bit of help in that. Unfortunately, he passed away late last year. But their memories as well as the achievements will carry on with us. Okay, with that done, firstly, we'd like to claim that Fugaku is the first exascale machine in the world. There are several definitions of what is meant by exascale. Some people say that 1 exaflop LIMPAC is the definition, and by that definition, Fugaku obviously is not. But some others claim that the performance of any metric, especially those that with actual running of the benchmark or applications exceeding an exaflop, will be an exaflop machine. In which case, Fugaku is an exaflop machine, exascale machine, because it achieved 2 exaflop in HPLI. But of course, then Fugaku is not the first machine to exascale, because Oak Ridge's Summit achieved exascale back in 2018 at Gordon Bell Prize. Well, I think what's most important, and also what's important for the project as well as HPC itself, is that it's not about these peak performances or demonstrated performances, but rather it's the speed up we attain from our past machines, which are considered to be, let's say, petascale or 10 petascale and so forth, last generations of machines. And then we have the pre-exascale machines now, but then Fugaku goes beyond not only those, of course, those 10 petaflop, like K computer, 10 petaflop scale machines by almost 2 orders of magnitude, but these pre-exascale machines by a few factors, which means that it has achieved exascale in terms of what's the most important metric, the applications. And Fugaku was designed with the applications first philosophy in mind. So with that, I think we achieved exascale with the most important metric, which is the applications. And I've said this repeatedly. Of course, it's not very easy to achieve this performance while being very useful in general, have very wide-ranging impact. As was mentioned in the opening, Fugaku is now used for hundreds of projects, both in not only in Japan but worldwide, immediately after its production commencing. And also we're expanding our usage to non-traditional domains, as I will describe later. and thus the name Fugaku, where it's very high peak, but also broad applicability, as the mountain signifies, Mount Fuji signifies. So, and this was not easy, but we spent 10 years designing and building the machine, and we achieved these top performance by this new ARM processor. And I think this you know very well now. And also, although this chip is very powerful, we also able to scale the machine to 160,000 nodes. And the power of Fugaku is almost equivalent to 20 million smartphones, which runs the same code, technically, because both the cell phones, smartphones, and Fugaku are both ARM-based machines. So they run the same code. They can run the same binary. And but performance-wise, Fugaku would be equivalent to about 20 million smart cell phones, which is about the number of smartphones shipped in Japan over the course of a year. So the magnitude of computing Fugaku would be equivalent to, a few Fugakus will encompass all the computing requirements in Japan. So that's the magnitude of the machine that the exascale machine brings. And of course, it's not just the CPU. We have world-leading advanced IT in terms of the processor itself being built, one of the first processors to be built with 7-nanometer technology. It still has the highest memory bandwidth for a general-purpose CPU, because it's the only CPU so far to be able to integrate high-bandwidth memory. Only GPUs and these more specialized chips have been able to use these, have high bandwidth memory, but none of the general purpose CPUs have been. It's still even 3 years after A2FX have been introduced. And of course, it's ARM compliant. But it's not only that. The other aspects of Fugaku is also demonstrates excellence, technological leadership. It's one of the first, it's probably the first mainstream servers CPU to incorporate not only a network interface, but also the entire network switches on the die. So because Fugaku has 160,000 nodes, Fugaku has 160,000 network switches, which allows it to have 400 gigabit class network per each node. And the total performance injection bandwidth, in particular, of the machine is equal to 5 to 6 petabytes per second, and with 0.5 microsecond latency across nodes. This is incomparable compared to any of the general purpose networks that we see, let's say, on a data center. And also system architecture-wise, in order to reduce this latency and make it very flexible, it was one of the first server chips to accommodate ultra-scale disaggregated architecture. So with that, as Tomita-san had mentioned, or Takuma-san had mentioned also, I think, that we were able to achieve #1 across benchmarks, various top-ranked benchmarks, not only the top 500, which you see on the left-hand side, which most of the mass media pick up, and they say who's #1 and so forth, which is fairly meaningless in its own right. Just excelling in one benchmark is not very meaningful. But rather, we were able to demonstrate excellence across a broad range of benchmarks, which are representative of even broader range of applications. And not only that, we were able to demonstrate several factors speed up compared to these traditional machines by factor 3, factor 5, factor 4. When AI, of course, some of the newer machines have accelerated matrix engines. But even so, we still attain leadership in this benchmark as well as on real applications. And again, these are ranging from dense linear algebra, sparse linear algebra, proxy for convolutional neural networks, and also big data processing using graphs, very large scale graphs. So just before Omicron variant hit, and as the Delta variant was winding down, thanks to the vaccination, SC21 had been held in St. Louis, and a few of us were able to go there, and it was held hybrid. SC was held hybrid because the infections were really low at that point. And although we had been awarded the number one status across the benchmarks for consecutive times editions in a row, all our receiving of the awards were virtual. But for the first time, we were able to go there the fourth time, and for the first time get these certificates physically. And this is one of the hosts of the benchmark, Dr. Jack Dungara, who, of course, everybody knows as the king of HPC. And we were very proud to have received this certificate on behalf of not only everybody who was involved in the project, the entire Japanese HPC community, but also our taxpayers as well, who sponsored the machine. But of course, like I mentioned, the real demonstrative value of the machine was not so much in the benchmarks. The goal was to achieve almost 2 orders of magnitude speed up as compared to K on these various fields which are important for the sustainability of the society, or so-called Society 5.0, and to conduct these digital transformations I will allude to later. And so Tomita-san was instrumental working with people like me and others to come up with requirements across these applications, which are, again, of important areas, priority issues or areas to Japan and also to people globally for sustainability, such as health and medicine, environmental disaster, energy, carbon neutrality, materials and manufacturing for advancing, to help these efforts, and of course basic sciences, which we should never forget. And so the goal was to achieve almost 2 orders of magnitude speed up, and on some of the apps achieve over 2 orders of magnitude, and we had actually achieved that average of almost 70x, something like 67x, I think, depending on what average you do. And so we have actually satisfied our goal. And again, it's general purpose. So of course, our software stack is improving day by day, but it was important to be able to run all these applications, which are very different from, let's say, 10, 20 years ago, and much broader on this machine. So not only we made the hardware broader by being compliant with ARM and to be able to exploit these very broad ecosystem, we also had worked to expand the ARM ecosystem towards HPC, and also to adopt these modern software stack, which are becoming not only important for the industry for serving some commercial web services, but rather also becoming very important for science and also for industrial usage in various areas, from big sciences for basic sciences to things like material informatics, to genomics, to medicine, etc. So the benefit of Fugaku is to be able to run not only the traditional HPC software stack, but to be totally standards compliant, to be able to run and also be able to tune these new breed of software stack, such as those in data analytics, cloud, various standard operating systems, and also things like virtualization containers, along with traditional HPC stacks, and consisting of like Fortran and C++ and so forth. So this has been, so people have had very good successes porting their software. But of course, as I'll allude to later, tuning the software is another thing, and that's what we're working on to make ARM and also especially the Fugaku and x64FX environment much more robust to performance gains. So, but thanks to this, not only to long-term planning, but because of generality and of course the science and industrial needs, the usage of Fugaku was, even pre-production, of course, was high, but then production started, it was slow, of course. Any supercomputer is very slow at the beginning, but quickly rose to the extent that in August, we got more than 82%, and in some instances, in September, we were hitting more than 90%, 95% job filling rate. Of course, we are like 98% in terms of the overall machine's availability, and then hitting almost over 90% constantly, continuously, and hitting somewhere close to 95. I think the average ended up something like 92%. So basically shows the popularity of the machine. So despite the fact that this machine is immense, as had been predicted in the feasibility study we had conducted with Fugaku a long time ago, that we would have much higher demand than what we can provide. Unfortunately, we were able to basically demonstrate this even at the very beginning, at the inception of the machine. Fugaku is an extreme high demand, and also the power consumption. We were able, initially when the project started, due to various reasons, the goals and the claims were set to be extremely conservative. And of course, because we set these really high moonshot level goals, but in case these goals had not been met, we had to be able to back off. So the government always said, and it was some initial studies suggested that the machine's power would be 2 to 3 times more than K. And of course, as the development had progressed, we said, well, no, that's not going to be the case. It's very likely we'll be matching fairly close to what K is. A little bit of increase, but we can also improve on cooling and so forth. So the overall data center power will not be that different from K, although a little higher, but not that high, maybe 20% higher or something, 20, 25% higher. And this proved to be true, actually. And so it turns out that the Fugaku's average is about 18 to 19 megawatts. K was somewhere 10, 15, so about 15 on the when it was highly loaded. So it's not that different. And if you include the improvement in cooling, the site power, the average was about 22, 23 megawatts. Is constantly about 22, 23 megawatts. Of course, when you measure the power at peak on one of the most power-hungry applications, it could go up to something like 35 megawatts. And of course, we prepare for that. But overall, on average, we're getting about 20 megawatts approximately for the machine. So the DOE, when it started, the exascale project said that, US DOE said that the goal was to achieve exascale at 20 megawatts. And of course, for DOE was Limpac exaflop. But, we said that's not very important, it's the applications, but achieve exascale performance to applications. So if you take that into account, we effectively had met the DOE goal of exascale at 20 megawatts in 2020, when the machine was already up and running and prepping for production. So, then as I said, Fugaku is not only in leading IT, but also in how it will be used. And there are many, many exemplars, and I will not, steal the thunder as will be presented by our colleagues in the subsequent talks. I will just introduce our COVID-19 efforts, and then what are the implications towards Society 5.0 before I move on to the future talk. So as we know, COVID is, of course, very rampant, and that's why we're having this conference, this symposium, unfortunately online. But of course, Fugaku was not standing still, and Fugaku was deployed to do the leading research on how to combat COVID-19. And we did a public solicitation. Well, actually, MEXT did the public solicitation with our help, and then in total 6 projects were accepted. And the characteristics of this is it spans from very micro molecular level simulations, let's say by this Professor Mochizuki, in which he was simulating doing a very large scale simulation on how the new variants, the COVID and the new variants, how the bonding power will be different. What are the mechanisms for its bonding power and how they would differ amongst the different variants? how strong the bonding is in a very accurate sense. And also to things, other molecular level studies done by Yuji Sugita and also Professor Yasuo Okuno, largely to contribute to studies of new drugs and antigens for COVID, but also to much more macroscopic, not just medical pharma, but macroscopic type of simulation. I think that's really unique to, somewhat unique to Fugaku. Epidemiology, as well as society level simulations. And one simulation that's really became famous, but also due to this have been able to contribute to the actual prevention of COVID spread, is the aerosol, very detailed aerosol simulations. And if you're interested, you can read our paper that's published on arXiv, and which had won the Gordon Bell Award, as I will describe later, and soon to be published as a journal paper. But also even to bigger, to a much bigger area, like the entire Japan, how the economy of Japan would be impacted by things like lockdown, when lockdown happens due to COVID. So I will just cover the aerosol because I think it's demonstrative. But all these efforts were fantastic, and all these efforts had consumed compute power significantly, to the point that many of these, not all of them, but many of these topics consumed as much computing power as number 2, number 3, number 4 machines in Japan for the entire year. So none of these projects were trivial. It's not like they can use 1% of number 2, number 3 machine, but it would consume the compute power of the entire number 2, number 3, number 4 ranked machines in Japan for the course of the year. So we would need like 4 or 5 of those just to cover this, but only by the power of Fugaku enabled that we would be able to accommodate these simulations to combat COVID. So again, to demonstrate one thing, because lack of time, Makoto Tsubakura's effort into COVID-19. Oh, by the way, as you saw, so he and his group have been developing this methodologies for industrial grade CFD, which covers from automotives to combustion to things like one interesting application is like sports. And as we know, maybe some of you have read reports that very happy news that Kobayashi-san had won the gold medal with this Olympic ski jumping last night. But he may have been. It's hard to claim what really worked, and of course it was by the enormous work and the talent of Kobayashi-san and the Japanese ski jumping team. But Fugaku may have played a little bit of role in simulating his jumps, as you see here. This is swimming, and also that's something that's also being worked on to improve our athletes, to help improve our athletes' skills. So it can be used for something like that. And there's been a long series of work, excellent scientific work, to come up with a methodology, which in theory, the first glance may be theory, like finite volume, hierarchical structure grid, but actually to make it really work, there are many problems, potential problems with methodologies like this. And Tsubakura-san's team have been very diligent in coming up with the solutions to make it really useful for industrial grade usage, applicable to areas where previously only unstructured methods, unstructured meshes were applicable. So this software cube have been used in many applications, like the automotives to carbon neutrality, combustion engines, to even city airflow simulations, or to combat things like heat, to analyze what's called the heat island, the warming up of air in the inner parts of cities when you build too many skyscrapers that block the wind. But one thing what happened was, so his people noticed, and one of his team members noticed that the combustion work they had been very detailed internal combustion engine simulations they were doing. The spraying of the fuel be gasoline or diesel, is basically exactly the same physics as someone coughing or speaking or singing. And then this spewing of the droplets and aerosols into the atmosphere. And you can see that the aerosols would basically stay in the air for a very long time, up to hours, and unless ventilated. And this primary, now the epidemiologists believe that this is the primary cause of transmission, especially with things like Omicron variants, where very small amounts of viruses can cause transmissions amongst people. So it's very important to analyze what's going on because we can't see the aerosols, and that's the problem. So there are many, both positive, both really, inaccurate scientific statements saying things like masks are totally ineffective, or or people say no, we're not, we don't need to fear COVID, up to the point where people are just too scared. Although even with the proper safety measures in place, because simply it's invisible. It's like one of the big reasons is that the aerosols, this transmission carrier, is totally invisible, so we can't see what's going on. And it's not just us. The epidemiologists, the scientists, couldn't really figure out what was going on for a very, very long time. So we were able to essentially do these accurate simulations using masks and face shields and societal situations. In fact, entire societal situations like this for the first time. And we were able to carry this out with companies, many collaborations from not only from the academia, but from the industry, such as Kashima Daikin, the aircon company, Dio Paper, which makes masks, and so forth. For details, Tsubokura-san have done many talks, and there are many opportunities to hear his talk, so I'll leave the details to him. But basically, we were able to generate the digital twins or in virtual space, and then run these detailed simulations. So a lot of people, I will allude to later, that a lot of people think that digital twins and virtual worlds was about collecting data in AI. And they forget about the simulation part, which is probably the most important component. And but if you think this is, I'm making this up, just go read any slide. It says Society 5.0 digital, and look for the word simulation. In a lot of cases, they don't exist because people are so naive about these things. So simulation is the most important component, and we have demonstrated by creating over 50 virtual digital twins with societal scenarios, run thousands of simulations, and consuming, like I said, effectively the entire tier 2 machines capability over the course of the year. So this has been reported in many newspapers, websites, web news, etc., not just in Japan but internationally. And we like to think, and it's also been incorporated into government policies for and guidelines for preventing COVID transmission. And as a result, we submitted a paper to Gordon Bell to the special prize for COVID-19. There were 2 categories this year, and then we won, fortunately, and that's Tsubokura-san. And that's me, of course. And we were very proud not only to have achieved this, but also on behalf of everyone who's been involved with Fugaku, and also to our taxpayers, that they have been able to receive the benefit of Fugaku so early to save lives and save society. Okay, so what goes on from here? Well, there are 5 pillars of research at R-CCS, and we are a research center. We just don't operate Fugaku, but we have excellent group of researchers, both in computer science and also computational science. And we are reformulating. We have reformulated our teams, and we're still in the process of reformulating to be able to push both the frontiers of both computer science and computational science, and also the machine operations, and also use the result, and also apply the results in collaboration with the society to have immediate impact so that in order to achieve our sustainability goals. So each of the teams, of course, will pursue their scientific excellence. But we also, collectively, the teams will work together, not only amongst ourselves, but with our partners outside, and also the industry and also the governments to basically drive simulations for Society 5.0. For that, we really need to think about not only traditional simulations, but also convergence of first principle simulations with the new methods like empirical AI methods and big data instrumentation for data science on these large-scale HPC systems. So some people claim these should be on separate machines, but that's totally that will not make sense because of the massive amounts of data we produce and the proximity. They need to be in proximity to very large-scale computing. These three elements need to be converged into a single machine. And not only that, ad hoc integration will not work, but we really need to have foundational science of computing that would merge these three elements both in a very fundamental way at the very deep foundational theoretical levels to pragmatic implementations on a real machine, and also to be used for real science and industry outcomes and societal outcomes. And we also are working to increase or broaden the effectiveness of Fugaku and also what we have built to broader IT ecosystem and also to very many applications. Because HPC, we believe, is fundamental to the future of IT from IoT to clouds. So we are stepping up benchmarking efforts and bench analysis efforts, and also to reflect that in improving software stack. Well, the immediate impact of this will be that, some people say, well, I compile I do my first compilation of Fugaku. It kind of works, but, it's not as fast as expected. And that's, of course, due to, some are due to some of the characteristics of the hardware, but largely it's the rather immaturity of the software tools. And of course, to some extent, the applications also have to adapt to the architecture to some extent. If you do that, you get your performance usually. And but we need to be able to make that process easy to eke out the best in the machine. And this is applicable not only to traditional applications, but to broader sets of applications. And then related to that, we will take these results and then we will investigate the new computing towards post-Moore, which will be primarily non-quantum. And people often forget that still will be the dominant computing paradigm for the foreseeable future. But of course, quantum computing will be important for some of the workloads. So we need to pursue that as well. So we're doing both in collaboration with our partners. So again, this is what the teams will look like in 2022, fiscal year 2022. We'll have three new teams on the computer science or science computing side. We will have I will relinquish my leadership of the high performance AI team to a new leader. We will also have a HPC performance team to really improve and not only improve Fugaku's performance, but also to be able to do the science of performance instrumentation and modeling and so forth. And also, we're planning to have a dedicated team that will serve as a bridge between all the application sciences and the systems to make Fugaku a true digital twin platform for Society 5.0. In April, we have merged Okuno-san's biomedical HPC AI-driven drug development, which was our big win from the other part of Riken. It's been a super merger coming together of the excellent work they do with in drug discovery, in silico drug discovery, using HPC and AI methods, with not only a platform, but many of the research that's been going on at the application area. For example, Sugita-san's molecular dynamics genesis, but many others. And also, we are enhancing our operations team to put more emphasis on software. We have a new team, we have a new unit starting October, led by Dr. Murai. to work on the various software issues. We even may have more teams coming on the operations unit. Also, as an outreach to Society 5.0, we just opened a new office in April 2021, where we have the Office of Fugaku Society 5.0 initiative. So this office is serving directly to tie the Society 5.0 needs to both our using Fugaku as a platform to our applications and research portfolio, but also to the systems aspects as well. So Society 5.0 is basically, Society 5.0 is digital transformation of many aspects of society using for the sustainability goals using digital means. It's not replacing the office paper pipeline by Japanese stamps or hanko with electronic stamps, which is, I think, not a very interesting example of digital transformation, but rather to really utilize the virtual twins or in cyberspace, which are driven by simulation and AI and so forth, to really make a difference, to employ new methods, new ideas, so that the society will be more sustainable. And because Fugaku basically includes all these portfolio of being able to do very accurate renditions of the real world in this digital twin, but also excellent in AI capabilities and also big data processing. So by tying together Fugaku and its portfolio of software and algorithms applications to the internet and cyberspace, we can really try to build infrastructure for Society 5.0 based on with Fugaku playing as one of the central leaders. In fact, it's not just when we think about these platforms, it's not just Fugaku implementing the physics of the real society, but also we need to incorporate the digital aspect also into the digital twin. So not only Fugaku needs to accommodate many of the capabilities of the simulations, like when you have a smart city, you need to be able to conduct earthquake simulations, you need to do traffic simulations or economic simulations, whatnot. You also need to be able to virtualize the IT itself, just like but cloud technologies do that. We need to be able to build 100,000 Arduino sensors, virtual Arduino sensors in the virtual city, and manage them. And these are basically but we can use the same technologies that's used in the cloud to virtualize the services. So we have all the ingredients, but we're still working on but we're working very diligently to make these happen on Fugaku, and these are some of the elements. So the ARM being general purpose ecosystem, we know that these Arduino sensor controllers are built with ARM, so you can run them. You can run them directly. You can have a virtual machine. You can have 100,000 virtual machines across Fugaku and accommodate these the software stack of Arduino IoT sensors, and then hook them up to a virtual network, 5G or 6G network, hooked up to a cloud, which is a virtual cloud, but it's a cloud nonetheless, and with the supercomputing embedded, and do all the data processing and so forth to emulate the society, and also to hook them up with high-speed links with new fiber links, terabits of bandwidth in the future, so that it can be connected to the real world. So we are working on something like that. One thing we really are still pushing very hard on is to improve the AI capabilities, because simulation, first principle simulation is one thing, but also, as we know, we need super training and inference capabilities of AI as a counterpart. And we are also making Fugaku cloud ready from that perspective, and also for utility for more general services. We also have worked on Fugaku's live streaming data processing capability. In fact, the first consumer of the client, this data processing built by Dr. Yamamoto of the unit, the operations team, is basically all the sensor data of Fugaku being live streamed onto this infrastructure, such that we can see now. You can see Fugaku's status, this gigantic machine, in real time on your web browser, and you can dig down to every detail of the data. So so this is instrumenting Fugaku itself, but we can instrument the virtual society using exactly the same technology. And also Fugaku 5.0 allocations in place. And we hope that one of the first proposals will be accepted to this to really drive the society of 5.0. But we still need to not only work on these technological pieces, but we really need to firstly establish the relationship between the first principle-based simulations and also empirical AI-based prediction and big data instrumentation, and how to assimilate the data between these components. So some of the teams are working on this, as well as our partners. Miyoshi-san's team works on instrumentation and first principle-based simulations, data simulation, but also starting to work on AI. But many of the application teams are actually working on the AI components. Just for example, Okuno-san's team, by these empirical convergence of amongst many application areas, and also our application partners in the that are based not only within the R-CCS but outside R-CCS. We can really drive this scenario both pragmatically, but also derive the first principle theoretical underpinnings of how these should be combined. For example, when is it good to replace first principle simulations with AI within a certain error bound? So those are some of the questions that need to be answered. Unless these are answered, it's really hard to build machines for the future. And of course, there are many application scenarios that are being considered. Data processing platform Oishi-san's doing. Tsubokara-san's applying some of his simulation technologies coupled with AI into various societal situations. My former team, now to be former team, is and will still continue to work on training 100,000, enhancing from a system side, enhancing Fugaku's AI to be able to train at 100,000 nodes on Fugaku, and and that's probably one of that'll make it the fastest AI machine in the world for training. In fact, we have demonstrated part of this with Fujitsu in the latest MLPerf HPC version 1.0 benchmark, which was announced at SC21 in St. Louis. We have achieved nearly twice the performance of the top GPU-based supercomputers without half, with the 5,000 GPUs or so forth. Using half of Fugaku, 82,000 nodes, we were able to do this. So you can see that the full Fugaku will be equivalent to somewhere in the region of about 20,000 latest GPUs, and thus get number one in the world. And I'll skip the details, okay, of this, but you can see this in some of the papers that are being published. So the lessons learned from Fugaku is that the proper project vision and management was good, and this advanced that we built this machine ourselves, not just relying on just putting together components, really paid off. The code design really worked to attain performance while being really while being really easy on resource consumption, like power, also money, and so forth. An ecosystem, adhering to a standard ecosystem really helped. There are some shortcomings that we have learned. Of course, not every project is perfect. Co-design, we may have focused too much on co-design, and that's leading to the generalization of obtaining performance across the applications much harder, a little bit harder compared to, let's say, Intel platform. And we're working to rectify the situation a bit. But that's a big lesson learned, and that's largely, I said, to immaturity of software stack, but also applications needing to adopt the machine is still, if you look at the architecture, is still too focused on classical HPC because a lot of these new focus came out later in the project. But we'll be able to adjust to some extent, but still, if you ask any computational scientist these days, do you think simulation is important? Yes, it's important. Do you think AI is important? Of course, it's important. Do you think data science? Well, of course, it's important. Okay, so it's all important. So we need to, it's to anticipate what goes on, what will happen in the future much better than we had done in the past. And also, one bad news is also we really must work harder to advance the applications themselves, because that'll be the final part of my talk. As we go to post-more, it's even more demanding for the applications to adjust in order to attain performance. Surely they will run on the system, but to enjoy the performance for next generation machines and beyond, the applications some of the applications may really have to change their thinking about the algorithms to use and so forth, and really need to encourage that and to help people do that. Not only to say we need to do it, we need to provide people with tools and by means and mathematics and algorithms to help people do that. Okay, so as we know, the Moore's law is ending, and we're already doing some studies. Masaki Kondo of R-CCS and Keio University, he's led a concerted efforts throughout the Japanese HPC community to assess the requirements, what the anticipated performance if we just go the conservative route, and and just say, okay, we're going from K to Fugaku, then we'll just stick with the plan and kind of do a evolution, a very conservative evolution of the machine, circa 2028. Then, of course, the results are not very promising. If you look at the flops, it's not very high. But it's not so much the flops. What's more important is that the total memory bandwidth is also not very high. It's 683 petabytes per second, even with very high power. And if you realize that Fugaku is 136 petabytes per second, it's only like factor 4 or 5. So it's not nowhere near like factor of 50 or 100 that Fugaku had achieved over K. So it's only, a few factors, up to maybe a 4 or 5. So what can we do about it? So what we really need to do is go back to the principles and analyze the machine, the future technologies, but also look at how the applications are, what are the bottlenecks, how the computing, and how can they be involved to exploit the characteristics of the future machines, and also learn from the history as well. So if you look at any application within a processor, there are largely 3 types of kernels, and these are very rough classifications. So there are compute-bound kernels, like the top 500. It can be various precisions and modern. There's not just classic. Some are modern, like the deep learning convolutional kernels. But majority of applications, as I will allude to in a moment, is bandwidth bound, like HPCG benchmark. Some are latency bound, like Graph 500, but it's not just the big big data codes, but something like unstructured meshes. Mesh codes often become latency bound. Now, the classic vector machine, like the Earth simulators in the 90s, basically covered the bandwidth bound applications. So they were sort of very specific to certain type of apps. Of course, they covered compute to some extent. It became number 1 on top 500, but quickly superseded by the American machines, which focus much on these fairly unmeaningful flops. Now, the COTS-based CPU clusters, which I had worked on, and also Sato-san and others had worked on in the 90s and 2000s, and culminated machines like Tsubame and Jaguar and K, and also K is a variant of that. Use standard memory technologies, but basically we attained performance by massive parallelism, by lining all the processors up. They're cheap, they're inexpensive. So we get the bandwidth by parallelism, we get bandwidth by compute by parallelism, and we get latency, fairly good latency, because these are, because these processors are designed also for latency workloads. And then, but then that wasn't scaling. We anticipated it will not scale, so we went to something like GPUs. They're variants, but the GPU won out in the end. And we became, so GPU-based heterogeneous machines also became somewhat, started to become popular. And I was one of the people who worked on this early, like Symposium 2. Also machines like ABCI I worked on, but also American machines like Summit, Frontier, they spelled that, Aurora, European machines like Pisnite. So again, so in this case, the GPU would be covering the compute bound and bandwidth bound. Also, but the CPU would be covering the latency bound type kernels. What we did with Fugaku was basically kind of retract from that a bit, but not so much to use these commodity CPUs off the shelf, but design a machine where the GPU workloads would design architecture that would, where the CPU cores would also behave like GPU cores, in order to cover not only the bandwidth-bound kernels, but also the compute-bound kernels by this very wide vectorization. So, so you can argue which one's better, GPU-based machines, heterogeneous machines, or CPU-based machines, but heterogeneity is now the core, essentially. But, the intent and how these workloads are covered are basically using very similar technologies like high bandwidth memory. What we haven't investigated are CPU machines covering bandwidth bound and latency bound. Because if you look at many of the bandwidth bound codes, they're very difficult to program to make it into a library. Whereas compute bound kernels, you call BLAS, or you call LAPACK. These are, because their interface is fairly narrow, they can be made into libraries or frameworks that are much easier compared to bandwidth bound or latency bound codes. So to cover the latter two using CPU and just cover the compute bound using GPU and matrix engines is the other way to go, but which have been largely unexplored area for the most part in the machines. And then you can go extreme and say, our domain-specific accelerator is used for HPC. There are many variants of accelerators, on-chip integrations, mostly like Fugaku, A2FX. You can use multi-chip packaging. You can use ONO to you can have specific machines. And there are many variants, but what I like to stress here is that accelerators are a means to the end and not a purpose by itself. So we really need to analyze. This is the first analysis, but we need to analyze even more deeply what the accelerators would be good for and what they're applicable and what are the shortcomings. So one thing we did was to analyze whether these matrix, how much of this matrix, as you see here, on the left-hand side, or how many kernels are compute bound. And we did this across many applications, from K-computer, from other applications from like US exascale projects and also spec benchmarks, and so ECP spec benchmarks and so forth. It turns out that you can read this in the IPDPS paper, but basically it says that the very little of the codes are reliant on gem kernels. So no matter what application people claim, okay, the reliance on dense linear algebra is very low on these machines, across these applications. So the flip side is, if you had a perfect speed up, if the gem performance would be infinite, right, you still get very little speed up in terms of the whole machine, maybe like 30% or so. So this means that majority of the applications are either bandwidth or latency bound, and this is analysis of the bandwidth bound. I'm sorry, it's in Japanese. So many of the applications are on the left-hand side of the roofline curve. So it's all called roofline curve. So what we really need to do is to not only increase the flops modestly, but to increase the overall bandwidth of the system. Now, this hasn't said anything about latency yet, but bandwidth of the system in order to increase performance of our machine towards next generation. And in fact, if you look at accelerated computing, again, going back to the principles, and I'm running out of time, so I don't know how much of this material I can cover. Tomi-san, when do I end? Like 15? Okay, never mind. So the reality of accelerated computing is the fact that
your presentation.
Yeah, is the performance will be always governed by Amdahl's law and Gustafson's law. Okay. Also, from the user's perspective, the computing system should be uniform with heterogeneous distribution hidden under the hood as much as possible, because modern IT involves massive software ecosystem. So it's very complicated to try to adjust to renew your applications into a totally new algorithm. So it's best to be able to be generally programmable, not to have people require ninja programmers to port your code. And moreover, it'll be covered no matter what you do. It'll be covered by Amdahl's law and Gustafson's law. And a lot of people claim that because smartphones are subject to speed up by Amdahl's speed up, by having incorporating these micro accelerated units. They say that's the future of HPC as well, but that's not really exact, because the smartphones are only governed by Amdahl, right? There's no Gustafson law involved. Whereas supercomputers, because they're massively parallel, the speed up is not only gained by Amdahl, that is to say, improving performance of the chip itself, but it needs to scale to very, very large numbers. And that's where these plethora of accelerators simply fail. Okay. And I won't have time to really go into this. If you're interested, I can have a whole lecture on this. But basically, just to give you a hint of what's going on, accelerators are subject to Amdahl's law, where the accelerator components will shrink and shrink and shrink until you hit this asymptotic maximum, where you only have the non-accelerator component left. And some claim that this was the limitation of parallel computing. But John Gustafson proves that's not the case by saying, well, you can weak scale, basically. If you do perfect load balancing, or in case the alternative case, when you don't require load balancing, they're independent parallelism, then you can parallelize all you want. The non-parallel, so the time to solution will be the same, will remain the same, but the non-parallel region in terms of performance calculations will become smaller and smaller. So ultimately, you get perfect speed up when you can weak scale perfectly. That's the Gustafson's law. And all the modern supercomputers are built with that assumption. Okay. So combining these, so when you achieve both at the same time, the simple answer is it becomes very hard, because the accelerated components become smaller and smaller and become very, very difficult to achieve load balancing, which is a prerequisite for achieving the Gustafson's law. Okay. So you need to achieve extreme uniform load balancing, or alternatively, independent parallelism. But when you have a plethora of these different accelerators, it'll be impossible to load balance, or at least very challenging. So you can't have all these accelerators come in at at varying parts of the workload and expect that you satisfy the Gustafson's law to scale. That'll be very, very hard, almost impossible. Okay. And that's why it's no accident that every successful large-scale accelerated supercomputers, especially even GPU machines, Fugaku, no doubt, have been built with uniform nodes. Okay. And then the dominant processing model is that you would delegate the entire kernel to either GPU, as I have mentioned in the past, right here, you identify, it's a bandwidth-bound kernel. On the GPU machine, I'll run it on the GPU. I'm not going to have CPU run it. Okay, that's what you do, and that's how you achieve. And because your machine is uniform, if you do proper spatial decomposition, you can achieve perfect load balancing. That's why every machine is built like that, and every successful algorithm is built like that. Okay, and there's a consequence of physical law. You can't avoid this. So that's why multiple heterogeneous domain space accelerator is considered harmful. However, there's one area where accelerator would be beneficial. And in fact, it'll be the whole computing needs to go that way. They need to go, we really need to go. The other message I will bring, and I don't have any time to explain this, I'm sorry. Maybe I'll have some other opportunity, is that we really need to focus on strong scaling. And the domain and accelerators may work in that area, but in fact, it's not just the accelerators. The whole machine, the whole algorithmic direction needs to go towards strong scaling for the future. Unfortunately, this is the artifact of how computing will be developing. Okay, so no matter what application we say, oh, we need more memory. We wanna. That's not the right direction. I'm sorry. Okay, and I will just. I'm sorry. I have no time to describe this and some of the work we're doing, and maybe if you can look at the slides, and also working on quantum future. But again, why it's promising, based on the Amdahl acceleration. It's the quantum computer is the only Amdahl accelerator that's feasible. But I won't go into details. Okay. So, very excited. We are working all these. Feasibility study 2.0 essentially will be starting April 22. Not just us, but there will be many. It'll be run by MEXT. Have many organizations involved. Of course, we'll try to get involved heavily, and we welcome your participation. We are hiring team unit leaders. We'll have new teams, units. We have many positions open. So details, Google the R-CCS homepage. I'm sorry I couldn't get to the last part, but the message is, we have to really do performance analysis, and that's why we are doing comprehensive benchmarking effort, and you're welcome to participate. And we also need to make software robust for people because they need to run very well on these machines. But on the other hand, because the direction of future computing is going, and because of the performance analysis we're doing, we really need to focus on strong scale. Okay, and because even if we increase memory, it's not so much we're lazy about this. We're saying even if we increase memory, it's not going to speed up your science. That's a fact. Okay, unfortunately. So with that, I'd like to end my talk. Thank you.